Let's continue with Calc 2 review. This is part 5. This problem is number 39 on the study sheet. It has n equals 1 to infinity of 7n factorial over n to the nth power. Now, when you've got a factorial, it is usually very useful to use the ratio test. So let's do that. Ratio test. That includes this. It's the limit as n approaches infinity of. Now you've got to turn all the n's into n plus 1's first of all. So you've got 7. Then you've got n plus 1 factorial. You've got n plus 1 raised to the n plus 1. And then you multiply by the reciprocal of the original. So n to the nth over 7n factorial. Take the limit of the absolute value of that and you hope that you get less than 1. If you don't, then you've got some other things to do. So first and foremost, 7 cancels. And n plus 1 factorial over n factorial leaves n plus 1. So that's all. Another thing that I notice is that I've got an n plus 1 to the first versus an n plus 1 to the n plus 1 power. So that's going to wipe out one of these powers. So at this moment I've got a limit as n goes to infinity of, what's left here, n to the nth over n plus 1 to the nth. That's it, okay? Well, they're both to the nth, so we have this. We have the limit as n goes to infinity of n over n plus 1 all to the nth power. Now, you can't really figure that out right away, so we've got to use some logarithmic work to try to find that limit. So, not logs, logs. So I'm going to say that y is equal to n over n plus 1 to the nth power. So the natural log of y is n times the natural log of n over n plus 1. If I find the limit of the log, then I can put it back. Now, as n goes to infinity, this is going to infinity, and this is going to the ln of 1, which is 0. So we're trying to get infinity times 0. Well, that's indeterminate, so let's deal with that. We need to try to make a fraction out of this. So I'm going to do that by taking this as the ln of n over n plus 1 over, and then 1 over n, okay? That is the equivalent. So now as n goes to infinity, that one goes to 0, and so does this one. So now let's find the limit as n goes to infinity of this, okay? Well, now it is 0 over 0, so we can use L'Hopital's rule. L'Hopital's rule, 1 over this, so I'm going to use some skills from algebra, just flip that over, times the derivative in here. Okay, so we've got a quotient rule. We're going to have 1 times n plus 1 minus 1 times n all over n plus 1 squared. Okay, so there's the derivative of the numerator. Derivative of the denominator minus 1 over n squared. Okay, so now what do? Well, we can cancel that, thankfully. N plus 1 minus n is just going to leave us a 1 here. So what do we have? We've got limit as n goes to infinity. So we've got 1 on top. We've got n plus 1. So n plus 1. Then I'm going to flip this one over. I've got minus n squared over 1. So I can cancel one factor of that. So I've got this. Now as n goes to infinity, this one goes to minus infinity, that one goes to plus infinity. L'Hopital's rule. So let's take the derivative again. So derivative of minus n, so the limit is going to be minus 1. Derivative of n plus 1, that one is 1, so we get minus 1. Okay, so what does that tell us? Well, it tells us that the ln of y was minus 1. So the ln of y was minus 1, which means e to the minus 1 is equal to y at that limit, and y was this. So the limit here is e to the minus 1. Now, what you've got to do is you've got to think, okay, what is e to the minus 1? Well, that is 1 over e. E is about 2.71828. So you've got 1 over almost 3, which is definitely less than 1. And if it is less than 1, we get what we wanted. We can conclude that we've got a convergent series. So it's got a little bit of extra work in it, but that one converges. All right, let's find some different things going on here. Let's see here. Let's find convergence or divergence of number 43. It's got n equals 1 to infinity. It's got minus 1 to the n. It has 4n to the 5th plus 8. So this is an alternating series because of the minus 1 to the n. And so alternating series test says that it's got to be alternating and the terms have got to go to 0 for convergence. Well, this denominator is getting bigger and bigger and bigger, so does it in fact head to 0? Yes, it does, so this one converges. So that one is relatively easy. Let's check some other ones. Let's find the Taylor series of a function. So this one's number 45. It has this. It's got f of x is equal to 1 over 7 minus x. And I want to center it at 6. So a is 6. And so let's find this. Now the hint here says to use a geometric series. So this is kind of fun to do. So if you've got a geometric series, here's what you have. You got a series n equals 0 to infinity of a r n. And if this works, if r, its absolute value is less than 1, so if that's the case, then the sum is equal to a over 1 minus r, okay? Now, I said center is 6. That's what we're going to use for this. Okay, I know I've got a in 2 different places, and that's a little bit strange. So let me rework this and call that C for center, because it's not this, it is the center. Okay, so first thing we've got to do is focus on that center. Notice this looks similar maybe to this. I'm hoping you notice that. So to make the center work out, let's go with this. We've got 7 minus, now we've got to have x minus 6. That's going to center it. But I just changed the value because I actually added 6 to the denominator, so I need to subtract 6 from the denominator. Now it's the same value that it was, so it's equal to 1 over 7 minus 6 is 1 minus x minus 6. So that actually looks a whole lot like this one, because it's got a number here, a 1 here, which is essential, minus a value r. So what was that series-wise? Well, it was ARN. So this is n equals 0 to infinity. What's A? A is in this slot, it is 1. R is x minus 6 to the nth power. So there's a series for that function. Kind of an interesting thing to do. Okay, now let's find a Taylor series for this one. F of x is equal to x squared plus 2x plus 5, centered at a equals 1, or c equals 1. I'm going to put c here. So, Taylor series. Well, Taylor series, just in general, we've got to find f of c. That's the first thing we do. So we put 1 in here. 1 plus 2 plus 5 is 8. Okay? Then we've got to find f prime of x, which is 2x plus 2. That is the first derivative. We have to find the value at c. So f prime at c is 2 plus 2, or 4. Then we've got to find f double prime, and that is 2. F double prime at c is still 2. So there's nothing we can do about it. And we're done, because the whole thing's kind of taken care of. Okay, so here's the series. We've got to have f of c, which is 8, plus, then f of our value, so f prime of c is 4, multiplied by x minus 1 to the first over 1 factorial, then plus f double prime, so that's 2x minus 2 squared over 2 factorial. So power and number of factorial. So the 0th, the first, the second. So that's all we get, okay? A lot of Taylor series are infinite. That one was not, because it was a polynomial. All right, let's keep going here. So let's find, let's see, let's go to parameterization. Just kind of work a little bit that way. So I've got a function. I've got an array with an initial point of minus 5, 4. So my initial point is minus 5, 4. And my terminal passes through 111. Passes through 111. Okay? And I have got to have some kind of a ray or line type equation. So I'm going to go ahead and say that this is the terminal point for this particular discussion. So the ray, call it a vector or array. So I'm going to call it a vector, okay? And so we've got to try to deal with this. We can tell some things about it if we want to. We can actually deal with the slope. Okay, what's the slope? Well, the slope is 11 minus 4 is 7 over 1 minus 5, which is 6. So there's the slope, okay? Now, they actually said to parameterize the curve. So, you know, I really don't want x and y here, but I could deal with that. So you could, and it actually says it's a half line, which, you know, half line, whole line, whatever. But if you've got a slope, you could write a line equation. So let's start out doing that, okay? So if we want a line equation, we've got a slope, we've got a point. So initially we would say y is equal to 7, 6x plus b. This is one way to do a line equation, and you may not do it this way at all, but this is something we can try here. Okay, so if we've got that, put one of our points in there. So if I put 111, I've got 11 is equal to 7/6 times 1 plus b. So if I subtract, I've got 66/6 here. If I subtract 7 of them, I've got 59/6 is equal to b. Now that's pretty boring, but anyway, we've got this line equation. We've got y equals 76x plus b. Now, plus 59/6. Now, that is not what they want, right? So, what you could do there, then, is you could try to find x as a function of t, and find it, and then have y as a function of t. Now, parameterization is not a unique scenario. So, one method that you could use, if you happen to have this, is you could do something, and this is super boring, but you could do this. You could say, okay, this one's t, and then this one is, look at this, 7/6t plus 59/6. Now, that is not very exciting, and it really doesn't work terribly well with this initial point and all that kind of stuff. So let me go back and do another method. Let's do this, okay? So here is another way that I really like to do this. I really am not all that fond of this one, but parameterization is, like I said, not unique. So let's say initial point. So when t equals 0, that's initial point, right? We have x equals -5 and y equals 4, okay? So let's then say when t equals 1, now that does not have to be that way, but I'm going to do that. Then I've got x equals 1, and y equals 11, okay? So how do we do that? Okay, well, how do you get, at time 0, how do you get -5? Well, one thing that you can do, here's x of t, okay? So if t is 0, you can have something with a constant of -5, all right? Now, how are you going to get +1 when you've got t is 1? Because you've got some number here times t. So if t is 1, then you're going to have 1 times something. You got to add 6, right, to -5 to get 1. So let's put a 6 there. Notice that's the denominator of the slope too, by the way. So what we've got is 6t minus 5. That's going to work. Now, y of t, same process. I'm going to put 4 as my constant. Now, how do I get 11? I have to add 7. So I'm going to call this one 7t. Notice the relationship there. Okay, so that's going to be 7t plus 4. So if t is 0, we get -5, 4. And if t is 1, we get 6 minus 5 is 1, 7 plus 4 is 11. So that's probably the way that would be a little easier to do some parameterization. And I kind of like doing that. All right. Now, another problem. This one's number 49. It's given in polar coordinates. It's got -2 pi. And we're supposed to turn it into Cartesian coordinates. So, where is this? Well, the angle is at pi, so that's this way, but it goes -2 units, so 1, 2. So it's right here, okay? So what's the Cartesian? Well, the negative pops it over here, so Cartesian's going to be what? 2, 0. All right? So that's kind of neat. You could use all the different formulas and such, but that one didn't really need too much work. How about number 50? Let's deal with that one. Number 50 says this. It says -9. So we've got -9. And then we've got 5 pi over 3. 5 pi over 3. Okay? -9, 5 pi over 3. Well, you know, that's trig again, as a general plan. So 5 pi over 3, that is pi over 3 reference angle here, because this is 6 pi over 3, so here's a 5 pi over 3. It's pi over 3 reference. And what do I know about this? Well, I know this length is minus 9. Okay, so I got to go this way, don't I? So that's really not where I'm going to deal with. So this one's 9. And this is my pi over 3 reference. Okay. So what do I know about x and y? Well, let's pop it out here. So if that's a pi over 3, then I know this triangle I just drew, it's in the second quadrant. So the cosine's negative and the sine's positive. The x value is going to be negative. Okay, so the cosine of pi over 3, here's the ratio. This cosine of pi over 3 is a half. Okay, so stick that in the second quadrant, we get minus a half. So how do we get minus a half when we go x over 9? So this is minus a half equals x over 9. So x is minus 9 halves. So x is minus 9 halves. Now what's y? Well, the sine of pi over 3 is square root of 3 over 2. So that has got to be y over 9. And that's actually a positive, so I just kept it attached. So multiply both sides by 9, you get 9 square roots of 3 over 2 equals y. So 9 square roots of 3 over 2. So you can use some of the formulas that are given and that sort of thing, but that's pretty easy way to go, okay? Let's look at number 51. See if I can get a new page going. We'll see what's going on with this one. Number 51 has this. It says that we've got the point 6 minus 4 pi over 3. And then we've got another point. It's minus 6, 5 pi over 3. And they're saying, okay, is this the same point? Are these two the same point? Well, let's try to find out. Okay, 6 units out on the minus 4 pi over 3 radial. So 4 pi over 3 minus 4 pi over 3 is this way. Okay, there's a pi over 3 here. So it's 6 units out there. So that's that one. Now what about this one? 5 pi over 3 radial. So it's here. It is this way, and it goes minus 6. So are they the same? Yes, same point. Okay, so kind of interesting there. Okay, that's enough for this video.